I'm very pleased, well, I would have been very pleased. We had invited Professor Colin Adams here. He's a knot theorist. He had his doctorate from Jim Cannon at University of Wisconsin in 1983, and now is the Francis Christopher Oakley III Professor of Mathematics at Williams College. And for those of you who are interested in research experiences and undergraduate research experiences, he directs the small program there, which is very popular and oversubscribed usually. He's the author of several books, including How to Ace Calculus, A Streetwise Guide, the Knot book, and one of my favorites, Why Not, featuring the female superhero, Knot Man. But I don't know what happened, because instead we got his cousin-in-law, Sir Randolph Bacon III, well-known British explorer, so very pleased to welcome instead Sir Randolph Bacon III.
Oh, thank you very much. Thank you so much. To this special presentation of the British Royal Geographic Society. And given how beautiful the weather is out, I appreciate very much you coming in. But I think you'll find it well worth your while. For I will tell you a tale that will make your blood run cold. Yes, it will make the tiny hairs stand up on your arms, your legs, and, well, anywhere else you have tiny hairs. Let's not go into it. Now, perhaps before I begin, might I suggest that anyone who needs to, please go out and use the facilities. For I would hate for anyone to lose control of their bodily functions during the more terrifying aspects of my talk. Anyone? Anyone? Very well. Don't say I didn't warn you. Now, I'm going to tell you a tale of adventure on the high seas. And I see a few old sea salts amongst you, but not everyone is quite as waterlogged as they. So I thought perhaps I should begin with the usual necessary nautical nomenclature. Love that word, nomenclature. So in particular, here you see my sloop. And up at the top here, you see the mast that's coming down, right here down the top. Can't see this very well, can you? That's all right. There's the mast coming down, and the jib, which is the sail, and the front, and the mainsail right there, and the hull, and the keel, and the rudder, and the boom. And then you see this rope right here. You still can't see that. That's too bad. Oh, there it is, yes. You see that rope right there? That's called the sheet or the main sheet. I don't want there to be any confusion later with a bed sheet. It's actually a rope. Very good. Now, my story begins on a beautiful summer's day, just a year and a half past. The birds were singing, the sun was shining, and I was in my sloop awaiting the beginning of the Cambridge-Oxford Regatta on the Thames. Now, this race dates back to the 14th century, and as such has quite a few traditions associated with it, involving a live pig, 14 kumquats, and quite a bit of marmalade. I won't go into the details, but leave it to say, it was begun with the traditional dunking of a deacon. He squawked a bit, and we were off. The wind was blowing well that day, my friends. I got a good lead up. My sloop was cutting through the water like a counterexample through an errant theorem. And in particular, I was happy about this, for I was hoping to avenge our loss the previous year to the Oxfordians, or Oxys, as I like to call them. They hated when I called them that. Not as much as when I called them oxymorons, but let's not go into that either. But in particular, I had a good lead up, and I had a lead over my arch nemesis, none other than Sir Roger Penrose, or Penny, as I like to call him. He hates it when I call him that. But in particular, I had a good lead up, and I thought to myself, well, perhaps now would be a good time to have a bit of sustenance. I always bring something to eat on these voyages, and this particular time I had brought along a flan. You know flan, kind of a custard? I brought along a flan made for me by my housekeeper, Mrs. Brown. Now, Mrs. Brown is perhaps the finest flan maker in all of Britain. Sometimes I say to her, Mrs. Brown, you're flantastic. We banter like that sometimes, though nothing's ever come of it. Probably just as well as far as Mr. Brown's concerned. But in particular, I had a bit of flan and a spot of tea. And then I thought to myself, perhaps now I should tack. Now, this is something you do when you're sailing. You tack. And what that means is you swing the rudder to the side, the boat veers suddenly, the wind catches the sail, the boom swings across quite violently. It's very exciting. However, as I went to do so, I realized that I had a bit of a predicament on my hands. For you see, there was a knot in the sheet. Remember, it's not a bed sheet, it's a rope. There was a knot in the sheet. And as any good sailor can tell you, you cannot tack with a knot in your sheet. However, my situation was not quite as dire as it seems. For you see, I had a bit of experience with knots dating back to the Falklands War. Do you remember the Falklands War? 1982, a bit of a dust-up between us Brits and the Argentinians, or Tinnies as we like to call them. They hated it when we called them that. That's what the war was over, in fact. But in particular, we decided that we should send the British British children to the United States for safekeeping. And as I was only 32 at the time, I was sent to Texas and put in the care of an extraordinary individual named Mel Slugbait. Mel Slugbait taught me everything I needed to know about survival in the woods. He taught me how to start a fire using simply a lighter and someone's lawn shed. He taught me how to wear a rodent for a hat, a live rodent. And he taught me how, if you run out of rations in the woods, you can always steal more from the other campers. The man was a genius, a flawed genius, but a genius nonetheless. And in particular, he taught me about knots. And I remember well him telling me about knots, and what he said was, I'm going to use this toy here to demonstrate. What he said was, if you have a string or something else like this, and if there's a knot in it, if it gets a knot in it, well then, you can always disentangle it just by sort of pushing on it and shrinking the end until eventually it becomes disentangled. However, if you have something like this and you tie a knot in it, and then you glue the two loose ends together by snapping it closed in a case like this, then perhaps you have trapped a knot on the string, and no matter how long you try to disentangle it, you might never succeed. Now, my situation was a little bit different than either of those possibilities, because you see, in my case, one end of my rope was fastened to the boom, and the other end was free. But that same system that he had suggested to just kind of pull it back and shrink it back suggested that I ought to be able to disentangle it. So I decided that's what I'd do. However, as I went to do so, things took a dramatic turn for the worse. Yes, the sheet hit the flan. Shall I repeat that line for you? The sheet hit the flan. What was once an easily gripped rope was now a slippery, slidey mess. So what was I to do? Well, I thought to myself, perhaps I could dip the rope, the sheet, over the side of my craft into the Thames and thereby cleanse it. However, as I went to do so, a strange sense of foreboding overcame me. A strange sense of foreboding overcame me. I don't know if it was brought on by perhaps eating too much flan, a bit of nausea, or perhaps the rocking of the boat was giving me a touch of seasickness. Or perhaps it was caused by the theme music from the movie Jaws that I was playing on my tape recorder for my entertainment. But whatever it was, it proved correct, for at that instant, a great white shark leaped out of the water, its teeth glistening in the sun, its every intention to make my arm into an appetizer. I leaped back, and instead of lunching on bacon, the shark ate sheet. As I lay on the deck, that's the last of the bad puns. As I lay on the deck, checking to make sure that I still had all 12 of my appendages, that's a separate talk, actually, to explain that. As I checked to see that I had all 12 of my appendages, I realized that the shark now had the sheet gripped in its jaws and was towing my craft down the Thames toward the open ocean. So you see now, I had two problems on my hands. Problem number one, I still had a knot in my sheet, and problem number two, there was a shark that was towing my craft down the Thames toward the open ocean. I decided to try to solve the first of those problems first. So I thought to myself, well, can I disentangle this knot that's in the line? And I realized that if it were an actual knot in the line, because the shark was attached, it would be somewhat unrealistic to picture myself lifting the shark out of the water and trying to disentangle it with the shark attached. So I decided instead to try to determine, perhaps this knot was not actually a knot at all. Perhaps it was a trivial knot. And I thought to myself, well, how can I determine whether that knot is a trivial knot? And then suddenly I realized that many years before, when I had been at Camp Slugbait, Mel Slugbait had talked about this very issue. Well, hey there, campers. How are you doing? It's good to see all all you British kids here. Sure glad to have you here. I hope you're enjoying yourself in the United States. I hope you enjoyed that breakfast. That was armadillo with maple syrup. It's a delicacy. Now, in particular, the most important thing if you want to learn how to survive in the woods is you have to learn how to make knots. And the fundamental question in knot theory is the question, how can we tell if a knot is really knotted? Now, in this case, we have a knot where both of the ends are fastened down, so they're fastened to each other. So I've got a knot, I've clipped it together like this, and I'd like to know, can I or can I not succeed in disentangling this knot? And I don't want to have to spend 3 years trying to do it and not knowing if 5 more minutes of work would do the trick, right? So I'd like to be able to tell, how can you decide if this particular thing can be disentangled or not? That's a really good question. All right, now we're not the first people to think about that. Many other people have thought about that. In particular, Kurt Rademacher, he's a handsome man, he thought about this. He was a German mathematician in the 1930s. And he said, well, if I want to decide if a knot is non-trivial or not, we call the knot trivial if you can disentangle it into the circle, and otherwise it's non-trivial. And if I want to decide if a knot is trivial, I want to look at these ideas here. And what he did is he said, suppose I have a picture of my knot, and there's a picture of the knot there, and I've got some moves that I can do in the knot. He didn't call them Rademacher moves, he was a modest man, but we call them that now. And one move you can do that will not open the knot up or anything, but it's a move I could do to deform it is, I could just put a little twist in it, just like that. And that's what that first move shows, and it's called a type 1 Rademacher move. It changes the picture of the knot, but it does not change which knot it is. All right, so that's a type 1 Rademacher move. Then we have a type 2 Rademacher move where you take 2 pieces of the knot and you slide one over or under the other, creating 2 crosses, but you can see how I could just unslide that. And I'm allowed to go either direction here. I can either create a little loop like that in type 1 or remove it, and I can create 2 crosses like that, or I can remove them, in the case of a type 2 move. And then we have one more move, a type 3 move, and the idea here is, I want to be able to take this back strand that you see going across the back there. I want to take that back strand, this is just not working, is it? I want to take that back strand, hang on just 1 second. Oh, there, you can see that a little bit. I want to take that back strand right across the back there. Can people see this little red thing? Yeah. Yeah, okay. So I'm going to take that back strand that you see right across the back there, I'm going to slide it past the crossing behind there, okay? And I could do that without having to cut this thing open at all. I could just do that, and it would just be a local change that I can make. You can also think about this as taking that top strand right here and sliding it across this way, and it gets up to there. So you can think of it either as moving the back one or moving the top one. And these 3 Rademacher moves will not change the kind of knot that you have, because I didn't have to cut it open at all in order to create those Rademacher moves that you see right there. All right? So let's look at an example here. So here's an example where what I'm going to do is I'm going to start with this picture of a knot right here. This is called the trefoil knot. And I'm going to do 2 type 2 Rademacher moves at the same time. I take a little piece here and push it across. I took a little piece there and I pushed it across. Take another piece over here and I'm going to push that across. Okay? So I created 2 type 2 Rademacher moves that increased the number of crossings by 4. The reason I did it is because now I've got a region right here where I can do a type 3 move. I'll take this top strand and push it over across the crossing. Right there, that's a type 3 move. And I get to this picture. Okay? Now I'm going to do a reverse type 2 move to get rid of these 2 crossings at the bottom. Pull that up, I get to here. Then I'm going to do a reverse type 1 move, and I get to here. I got from this picture all the way to this picture by Rademacher moves. That means these have to represent the same knot. If I made them each out of string, I could rearrange one to look like the other. All right? So that's what that tells me, is that these are really the same knot, but these are just different pictures of the same knot. When I get a set like that that's related by Rademacher moves. All right? So now here's the amazing fact. And what it says is, it says if you have 2 different pictures of the same knot, they have to be related by Rademacher moves, okay? In that example that we saw, we didn't start with one, and we got to another one by Rademacher moves, but any 2 pictures of the same knot have to be related to a sequence of Rademacher moves. So here I have a picture of a knot, and then I go through, and I go, well, there's a 1 move, 2, 1, 2, 1, 2, 3, 1, 2, I don't care what they are. And when I get to the end, actually I'm going to have the same knot, and the only way that those 2 knots can be related is if there's a sequence of Rademacher moves. So that says if you want to decide if a knot is trivial or not, all you have to do is check and see whether or not there's a sequence of Rademacher moves that take that picture to the trivial knot, to the circle. That's all you have to do, okay? So here's a good question. Do you think that this knot right up here is in fact equal to the trivial knot? Could I rearrange it to look like the trivial knot, all right? And we're going to use a time-honored tradition in mathematics. mathematics, and that's called democracy. Okay? So we're going to decide the truth of this based on voting. Okay? This is what you do in math when you're trying to prove whether a theorem is right or not. You take a vote, and if more than half people say it's right, then you say it's a true theorem. Okay? So I want everybody here to decide, do you think this knot is the same as that knot? Do you think that this one could be rearranged and disentangled to be this one? Okay? How many people, raise your hand if you think so, how many people say, yes, you could rearrange this to look like that? How many people say yes? Okay. Okay. Pretty good number. How many people say no? I have to say, I think the yeses actually had more votes. And that's a good thing because, in fact, it is true, okay? You can rearrange it, but it's hard to see, and you shouldn't be embarrassed if you didn't get it. Here's the trick, actually, on this one. See this overstrand goes right over here to here, okay? If you took that whole overstrand and you stuffed it through this hole, you could simplify things, and then you stuff it again, stuff it again, stuff it again. It's hard to see, but in fact, you can do it, okay? You can rearrange this thing. But if you try to do it in terms of Rademacher moves, you have to actually increase the number of crossings. You can't just simplify it, simplify it, simplify it. You have to increase the number of crossings before you get down to the trivial knot, okay? So that's a bad sign because you're saying, well, gee, how am I going to then be able to tell whether or not the knot is trivial if I have to actually increase the number of crossings before I go down to no crossings, okay? So, luckily we're in luck. Well, there's an amazing theorem, okay, that says if you have a picture of the trivial knot, okay, so it doesn't look like a trivial knot, but it's got n crossings in it, like that last picture we saw, then it can be turned into the trivial projection in no more than 2 to the 100 billion n Rademacher moves. Okay? Isn't that good news? Right? Because that says, in the example we were looking at, if you were trying to show that this knot was not the trivial knot, all you'd have to do is check every sequence of 2 to the 100 billion times 7. There's 7 crossings there. So you just have to check 2 to the 700 billion Rademacher sequences, the sequences of length 2 to the 700 billion or less. And if every one of them did not take the one knot to the other, then in fact it's not a trivial knot. Okay? So that's all you have to check, okay? Now, this paper here, you see the number of Rademacher moves needed for a knotting by Joel Haas and Jeff Lagarius appeared in the Journal of the American Math Society in 2001. I know some of you are sitting there saying to yourselves, wait a minute. I thought you were Mel Slugbait from the year 1982. How could you possibly know about this paper from the year 2001? Well, what you have to remember is I am not Mel Slugbait from the year 2001, or from the year 1982. I am Sir Randolph Bacon III's memory of Mel Slugbait from the year 1982, and as such, he can make me say whatever he wants. I have no control over that. Okay? So anyway, the bad news is this is not a very good way to tell whether or not a knot is trivial. Okay? Pretty hard because you're going to have to check a lot of stuff. And this isn't checking 2 to the 700 billion things. This is checking every sequence of Rademacher moves of length 2 to the 700 billion. So that's kind of a big number. All right, so what else can we do? We're going to try a different system now, okay? A different way to tell whether or not a knot is trivial. And what we're going to do is we're going to tri-color it. So this is going to use crayons to do this. We're going to tri-color the projection. And what that means is we color the strands in our picture 3 colors such that 2 things hold. Number 1, at each crossing, we're going to either have 1 color at that crossing or 3 colors at that crossing. And what this is going to mean is we're not going to have 2 colors at the crossing. We'll have either 1 color at a crossing or 3 colors at a crossing. Okay? And then the second rule is you got to use at least 2 colors. Okay? It's cheating if you just make everything red. That would not be fair. Okay? So that's the rule. So let's try it. Let's see how it works. So here's a great example. This is another picture of the trefoil knot. And you'll notice when I draw it with 3 strands. So what I mean by strands is things you draw without taking your pencil off the page. So there's 1 there that I would draw without taking my pencil off the page. 1 there and 1 there. I colored this one red, colored this one green, colored this one blue. At this crossing, I have 3 colors. At this crossing, I have 3 colors. At this crossing, I have 3 colors. And I used at least 2 colors. So that is a valid tricoloration of that picture of that knot. Okay? Let's try another one. Here is a famous knot called the 7-4 knot. And on this one, we've got 3 colors here, 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 1 color there. But that's fine, I'm allowed to have 1 color. I'm just not allowed to have 2. So that's a valid tricoloration of that picture of the 7-4 knot. All right, let's try one more example. Here, I'm pushing the wrong button here. Here's what's called the composition of 2 knots. I took 2 knots, cut them open, and glued them together. All right? So I got on the left the trefoil knot. So on the left here, I got the trefoil knot. And on the right, I'm trying to get this. Here we go. On the left, there it is. On the left, I've got the trefoil knot over here. On the right, I've got what's called the figure 8 knot. I took the tricoloration that was for the trefoil knot, so you remember I tricolored that right up above there, and then I just extended it and made it all red on the other half, okay? And that's a valid tricoloration, because I got 3 colors, 3 colors, 3 colors, 1 color, 1 color, 1 color, 1 color. So that's kind of interesting that I can get away with that trick, okay? So that's another one. Now, but now you're saying to yourself, oh, wait a minute. Maybe you just tricolor every picture there is. This seems kind of pointless, doesn't it? We're just going to sit around with crayons all day. But don't worry, because here's some examples that cannot be tricolored. Example number 1 is the trivial knot. Okay, so the picture of the trivial knot, 1 circle. And the thing that's wrong with it, it's true at every crossing I have 1 color or 3 colors, because there are no crossings. But I did not use 2 colors, right? It's only got 1 strand, and I did not use 2 colors. So that fails to be a valid tricoloration. Okay, that's going to be kind of critical. But let's see another example. Here's another example. This is the figure 8 knot. And on the figure 8 knot, you have to try it. You get on here and you say, okay, I'm going to make this red going around here to here. This is red. I'm going to make this green, and I'm going to make this blue. Green and blue means this is red. And look at this crossing. I only have 2 colors. I don't have 3. If you just try it, you'll find out very quickly. The other option would be to make this whole crossing green up here. Green, green, green. That forces this green, forces this green. The whole thing's green. Doesn't work. So that has no valid tricoloration whatsoever. So there's nothing you can do about that. So that one's not going to work. Okay, so now, what can you do with this? Well, it turns out that if you have a picture of a knot and it's tricolorable, then every single picture of that knot is tricolorable. Okay? It doesn't depend on the picture, it just depends on the knot. Okay? And I'm going to prove that for you right now. It's actually really easy to prove. I'm going to prove that if you have a picture of a knot and it's tricolorable, you go to a different picture of that knot, it's still tricolorable. And the way we're going to prove that is we're going to use the Reidemeister moves. Because we already said if you have 2 different pictures of a knot, they have to be related by a sequence of Reidemeister moves from one to the other. All right? So I've got a sequence of Reidemeister moves. Let's just see what the Reidemeister moves do for tricolorability. All right? So type 1 move. Well, at the top it's all green. Then when I go past and I create this little loop there, I'll just keep everything green. And this is one of the crossings that has 1 color on it. And if this thing was tricolorable, imagine the rest of the knots hanging off here with lots of other colors on it, then the new one's going to be tricolorable, and vice versa. If I have this one over here, I can go over here. This one's tricolorable, this one's tricolorable, this one's tricolorable, this one's tricolorable. Okay, so that's the first type of Reidemeister move. Second type of Reidemeister move, there's 2 cases. If both the strands have the same color, when I slide the one over the other, I'll just keep everything green. If this one was tricolorable, this one is tricolorable. If the colors are different, when I slide the one over the other, I'm going to create a new little section of the 3rd color, in this case red. And now I have a tricolored vertex, tricolored cross in there, and a tricolored cross in there. And so I can go either way on these. So type 2 moves also preserve tricolorability. Okay? 1 move to go. Type 3 move. Let's see what happens with it. Well, it turns out there's a bunch of cases you have to check. You imagine that you tricolored things like this locally in your picture. So imagine I have a red there, a blue there, etc. Then when I slide this strand down behind, I'm going to change the color on this intermediate part right here and change it to blue right there. Now, important point here is I cannot change the colors of the strands going out because they're attached to the rest of the knot, which already has set colors. So I have to preserve the colors on the outgoing strands. But I can change that intermediate strand right there to a different color, and this is a valid tricoloration of the result. Here's another case right here. I've got 2 green strands and a middle strand, and I just slide it down and I keep the color of the intermediate strand the same. And you just check the cases, and once you check the cases, you'll see that in fact tricoloration is preserved by the Reidemeister moves. So if I have 1 picture of my knot over here, there's a sequence of Reidemeister moves to any other picture, and each one of those Reidemeister moves will preserve the fact it's either tricolored or it's not tricolored. All right? So that says, so let's take a look at how you can use this. I'm going to prove a fact which you've probably never seen before, which says there is such a thing as a non-trivial knot. Okay? It says that this knot, called the trefoil knot over here, which is the one I happen to have right here on here right now, this knot is not the same as the trivial knot. They are distinct knots. Because you can never rearrange this to look like that one, because that one's tricolored, that one is not. Okay? So there is a non-trivial knot. It took mathematicians a long time to prove that. But there is, in fact, a non-trivial knot. Okay, now how else can we use this? Well, you know, have you ever been to a magic show and a magician will say, I have 2 rings here, and they hold them out and they say, can you check and see those rings are really hooked together there? It looks pretty good. Not cheating in any way, right? Okay, so they're hooked together, and they say, now I'm going to show you an amazing trick, and they go, abracadabra! And the rings come apart, and everybody's like stunned that this actually happened. But the truth is, people should not be stunned by that, because the magician never proved that two rings hooked together are different than two rings separated. They never proved that. So you're like, well, so what? Who cares? You need a proof of that, okay? So what they ought to do is they ought to explain why it is that those two things are distinct. And the reason those two things are distinct, it amazes me, is that the trivial link of two components is tricolored, and the Hopf link, which is the links when the links are hooked together, is not tricolored. It's exactly the opposite for what happened up above. All right, the trivial link, there's no crossings, and I used two colors. That was why I said that the condition is you have to use at least two colors. I used two colors here. This one, if I try to tricolor it, I make it green all the way around. That forces the other one to be green too, because I can't use two colors, and then I have to use two colors. Okay, so they're distinct. Okay, so magicians ought to do that. They don't, but they really ought to. All right, so now I think I've said enough. You get the idea, this idea of tricoloration, being able to tell whether or not knots are trivial or not. Now I want all you British kids, I know you're really excited to be here. I want you to go off and play in the woods, but if you're not back by dinner time, I will send out the dogs. Okay? So there you see, I realized that all I needed to do was to check whether or not my particular knot was tricolored, and if the knot was tricolored, I would know immediately that it could not be the trivial knot. So I pulled out my crayons that I always bring with me on a voyage like this, and I actually went to check. And as I went to check, I started up here, and I colored this part up here green. Then I colored this part red. And then I had to color this blue, because I needed three colors there. Red and blue forces this to be green. Red and green forces this to be blue. Green and blue forces this to be red. And then you see there's a crossing with two colors on it. It didn't work. It did not work. So then I thought to myself, well, what if I start with green, and then green, and then green, and then green, and the whole thing turned out to be green. And so therefore, there was no tricoloration. And not having a tricoloration does not tell you anything about the knot. It does not mean it's trivial or not. So perhaps it's trivial, or perhaps not. So I was very disappointed to realize that this particular technique didn't work. But then, I remembered that Mel Slunbait had continued his discussion of this issue those many years past. I know you can see me. Well, hey there, campers. I hope you enjoyed that breakfast. That was pine cones with maple syrup, another American traditional breakfast. Now, you'll remember yesterday we were talking about this idea of tricoloration and using tricoloration to distinguish knots one from the other. And unfortunately, I didn't get a chance to say this yesterday, but it doesn't always work. Sometimes it's not enough. So you need something more in order to actually show that two knots are distinct. And so we're going to go up to the next level, which is called modular arithmetic. And I know a lot of you here are familiar with modular arithmetic, but some of you may not be. You British kids, I know you've all seen it before. And the idea is, it's like clock mathematics, modular arithmetic. And the idea is, when you're telling time, like if you're in the military, they use this idea in the military, right? And they'll say, okay, I want you to go clean the latrine in 1400 hours, right? And you know what that means is you say, well, what they mean is, if it's 1400 hours, what you do is you take that 14 and you subtract off 12, and you get 2, because 14 and 2 differ by 12, and therefore you know I'm supposed to go clean up the latrine at 2 o'clock. Okay? That's how you figure it out, okay? Or they might say, we're going on a 20-mile hike at 2700 hours. And you say, well, 27, if you subtract 3 from it, it's divisible by 12, so that means 3 o'clock. So I better be ready for that hike at 3 o'clock, okay? Or you might say, okay, I want you to peel every potato in this camp at, negative 800 hours, okay? And negative 8 differs from 4 o'clock by 12, and so then you know those 4 o'clock when you have to do that, okay? So that's the idea of modular arithmetic or clock mathematics, all right? So in particular, we just say A equals B mod P if P divides the difference between those two numbers. If P divides the difference between those numbers, 7 equals 2 mod 5 because their difference is divisible by 5. 9 equals 0 mod 3 because 3 divides 9 minus 0. And 1 equals 7 mod 6 because 6 divides 1 minus 7. Okay? Now we're going to use this idea to try to figure out whether or not knots are trivial. And namely, we're going to use what are called P colorations. And what we're going to do is we're going to label our projection, instead of with 3 colors, with P colors. Okay? And those are what I'm going to denote them. Instead of denoting colors, I'm going to denote those by integers 0, 1, 2 up to P minus 1. And now I'm going to have a condition at each crossing. You remember the old condition was you can't have 3 colors, you can't have 2 colors. You can't have 3 or 1 color. Now we're going to switch it. We're going to say, okay, if I've got 3 labels, which are my colors, A, B, and C coming into a crossing, I want them to balance. Namely, I want A plus B, these are the 2 colors coming in this direction and this direction, equal to C plus C, which is 2C, mod P. So I picked a particular P. I'm doing a P coloration, and I want A plus B to be equal to 2C mod P. And I have to use at least 2 colors. All right? So let's try this. Here's the figure 8 knot. You remember it did not have a tricoloration, but it does have a 5 coloring. So I'm going to label its strands 0, 1, 2, and 4. I don't have to use all the colors. I didn't use 3, you'll notice. 0, 1, 2, and 4 at the top crossing. 0 plus 2 equals 1 plus 1. 2 equals 2. So it satisfies that condition. 4 plus 1 is 5, equal to 0 plus 0. Well, 5 equals 0 mod 5, because they differ by 5. Okay? Then I look at this crossing down here, and I get 1 plus 2 would be 3, and that's supposed to equal 4 plus 4. 3 is supposed to equal 8 mod 5. They differ by 5, and so 3 and 8 differ by 5, so that's okay. And then finally, the last crossing right here, I've got 0 plus 4 is supposed to equal 2 plus 2, and that's true mod anything. And 4 is equal to, that's right, 4 is equal to 2 plus 2. All right? So that's a valid 5 coloration of that particular knot right there. All right? And just as we saw for tricoloration, I should have said this first, it turns out a tricoloration is a 3-colorant. That's not immediately obvious, so let's just talk about it for a second. If I have a crossing that just has 1 color on it in a tricoloration, then all 3 of my labels are the same, and it will be true that A plus A will equal 2A. Right? So that's certainly going to be true. And if I have 3 different colors on my 3 strands coming into a crossing, then I'm going to check whether A plus B equals 2C, mod 3, and I just check the cases. I say, well, what if the first one's 0, the second one's 1, and then the third one must be 2, and it is true that 1 is equal to 4, mod 3. And then I might take 1 plus 2 equal to 0 mod 3, that's true, and I just check the cases. Okay? And it turns out that it's true. So a tricoloration is just an example of a 3-colorant. All right? And just like for 3 colorations, just like for tricolorations, these P colorations are preserved by Reidemeister modes. So if I have a picture of a knot, another picture of the knot, and the first one's P colored, then the last one's P colored. Okay? Just depends on the knot, does not depend on the particular picture. And in particular, that means that if one knot, a picture of a knot is P colorable for some P, then every picture of that knot is P colorable. Okay? And then finally, the thing I really care about is, if I have a picture of a knot and it's P colorable, then that knot has to be non-trivial. Because the trivial knot does not have a valid P coloration, because it only has 1 strand that you can label, and you have not used at least 2 different labels, at least 2 different colors. Okay? So that's what I care about. If I can get my particular knot to be P colored for some P, then in fact the knot has to be non-trivial. All right, so I'm going to send you out in the woods again, but if you're not back by dinner time, I will send out the dogs. Yeah, so now you'll see, I realized that all I needed to do in order to determine whether or not this knot was trivial is to try to decide whether or not this knot had a valid P coloration. So I pulled out my colored pens, and I'd already tried it with a 3 coloration, that didn't work. I tried a 4, I tried a 5, I tried a 6, none of them worked. But then I tried a 7 coloration. And you see here, the first crossing that you see right there, you'll notice that 0 plus 2 is equal to 1 plus 1. So that one is fine. This is going to be mod 7, but it doesn't matter in that case. 0 plus 2 equals 2. Here I had 1 plus 3 equal 2 plus 2. That's certainly true. 4 equals 4. Here I had 1 plus 5 equal to 3 plus 3, which is 6 equals 6. That one was fine. Here I had 3 plus 0 equal to 5 plus 5, namely 3 equals 10 mod 7, because 3 and 10 differ by 7. So that one was okay. And then finally the last one up at the top here, I had 2 plus 5 is 7, which is equal to 0 plus 0. 7 equals 0 mod 7, because those 2 numbers differ by 7. So then I realized I had a valid 7 coloration, and I was was so excited and happy until I realized that it was bad news. For this particularly told me that the knot was non-trivial, and no matter what I did when that shark was still attached, I couldn't possibly succeed in disentangling this knot. I was so frustrated, without even thinking, I leaped over the side of my craft onto the back of the shark, and I began to pound the shark's back with my fist, and the shark began to thrash about and chew through the sheet as he did so, and I leaped back on my craft, and the shark disappeared into the waves. I dare say never to bother any Englishmen again. As I lay on the deck of my craft, breathing heavily, so relieved, now far out into the Atlantic, I heard a noise in the distance. It sounded something like this. Yes, it was thunder. What had begun in California as a sneeze by Arnold Schwarzenegger had grown into a low-pressure system that crossed the United States and collided with a hot air mass over Washington, D.C., and then moved out into the Atlantic to create perhaps the greatest storm ever to hit the Atlantic, greater even than the so-called poorly named perfect storm. I nicknamed it the especially perfect storm. The wind began to howl. The rain began to pour. Oh, sorry, the birds began to tweet. Excuse me. I realized I was in serious trouble. I had to do something quickly or it would be too late. So I thought to myself, I could hardly hear myself think, so I thought I would turn this down just a tad here. So I thought to myself, well, perhaps I could try the following trick. Perhaps I could take my knot and I could tie a second knot in the line. An inverse knot, if you will. A knot that would come together with the original knot and would annihilate it. And the two would disentangle each other. I thought, of course, this is what I should do. And then suddenly I realized that couldn't possibly ever work. Because you see, the new knot also has a valid tricoloration. I could take the tricoloration that I had on the original knot, and then when I tied the new knot in the end, you'll see I could extend it across just by using whatever color I had here everywhere, and that would be a valid tricoloration, and therefore I could never be trivial. Of course, most of you already knew this. I doubt very much that when you pull an extension cord that's all tangled out of your closet that you tie a second knot in the line, hoping to disentangle it. So I needed help, and I knew it now, and so I decided there was only one thing left to do. And so I pulled out my cell phone. You'd be surprised how good the coverage is in the Atlantic. And I called my old mentor, Mel Slugbait, in Texas. Excuse me just a second while I get him on the line. Yes, hello. Hello, is this Mel Slugbait? Yes, hello, it's Sir Randolph Bacon III. Yes, that's right, little Randy Bacon. Yes, I'm all grown up now, Mel. Yes, I'm in a bit of a pickle here. You'll see I'm out actually in the Atlantic in a small sloop, and I have a knot in my sheet. It's a rope that hangs off the boom, actually. Yes. What's that? You want me to describe the knot to you over the phone? Very good. You see it's got a bit of a protuberance on the upper left, and another one hanging off the bottom, and then a bit of a bump on the right. Oh, you want me to describe it using the Dowker-Thistlethwaite notation? Of course, how silly of me. Just hang on just a second. I'd completely forgotten that he taught us a notation for describing knots over the phone. Wait, this is the fun. What you do is you get on the knot at some point, you move along, and each time you come to a new crossing, you put a new integer in order 1, 2, 3 as you go along at each crossing. So I start right here, and I come up to here, and I put on my first integer right there. So I put a 1 there. Then I go on again to the next crossing, and I put an integer there, 2, to the next crossing 3, to the next crossing 4, to the next crossing 5. Now you see I come back to a place I've already been. I don't care. I'm going to put 1 there again. 6, to the next one, 7, to the next one, 8, to the next one, 9. I pass through each crossing twice, so every one of the crossings gets 2 integers, and off I go. So now I've put these 2 numbers on each of the crossings. And in fact, it turns out, you can check for yourself, it's actually not that hard to prove. You will always get 1 odd number and 1 even number at each crossing. So now what I'm going to do is I'm just going to list the odd numbers first, and underneath them, the even number that was paired with them. Now, the odd numbers on the top are always going to be the same, so I don't really need those. So I will just keep that permutation of the even integers on the bottom, and that should be enough to describe my knot. Hang on just a second, let me give it to Mel on the phone here. Yes, hello, Mel. The knot is 6, 10, 8, 2, 4. Now, at the other end of the line, Mel does the following thing. He says, okay, if it's 6, 10, 8, 2, 4, then what I'm going to do is I'm going to write the odd numbers above those, 1, 3, 5, 7, 9. And now I know that the first crossing must be 1, 6. And so he creates a 1, 6 crossing that you see right there. Then he goes to the next one and he says, well, the next crossing is going to be a 2 as I move across, and 2 is paired with 7, so I put on a crossing that's a 2, 7 crossing. The next crossing will be 3, which is paired with 10. The next crossing is 4, which is paired with 9. The next crossing is 5, which is paired with 8. The next crossing, as I keep going in this direction, 1, 2, 3, 4, 5, the next crossing I'm going to get to is 6. I have to come back around to 6. And so I come back around to 6. Then I'm going to go around to 7. So I come back up here to 7. Then I'm going to go from 7 all the way over to 8. So I have to go from 7 all the way over to 8. So I go over to there. 8 goes to 9. 9 goes to 10. And now I'm done. So now he's created the knot, and he can look at it and try to tell me to help me. Let me see what he has to say. Yes, hello, Mal. Can you help me with this? I'm in quite a dire situation. What's that? You're kidding me. Really? You're telling me that if I simply take that central strand that runs all the way down this picture you just created, if I simply take that strand and pull it straight through, that will disentangle the knot? That's all I have to do? And then suddenly all the crossings are gone and it's not tangled anymore? That's brilliant. Thank you so much, Phil. Let me go back for just a second. So you just take that entire strand all the way down, pull it all the way through, and the knot is no longer tangled. Thank you so much for your help, Mel. I really appreciate it. He was absolutely right. That's all I had to do. And so I did it. And now I was free to sail and bail as if my life depended on it, which in fact it did. And I matched wits with this greatest of storms, this amazing, especially perfect storm. And luckily, although it was big, it wasn't that smart. And I won that battle of wits. And I lived to see another day, washed up. I washed up on the shores of the French Riviera. Just in time for the Cannes Film Festival. Now, I won't bore you with my adventures there with Danny DeVito and Angelina Jolie, but leave it to say that I do have a movie deal with Paramount Pictures. But unfortunately, I did lose that regatta that day, and Sir Roger Penrose, or Penny as I like to call him, received one more trophy to put on his mantelpiece next to all the other trophies. On the other hand, who would you rather be? I had an amazing adventure, and I had to think about mathematics. So who would you rather be? Me or Penny? Thank you very much for listening. I'm just going to run the credits. If you just hang on for one more second.